So we'll begin by me telling you a story. And I think this story will help illustrate what power is and some of the various things that go into calculating power. So most of you probably don't know, I am a little bit of an amateur astronomer. Not in real life, just for this example. And I'm interested in all things outer space. Trust me, there's a point to this story. So I heard that there is an asteroid flying by on December 1st between Earth and our nearest neighbor, Mars. And this is a once-in-a-lifetime event. This asteroid only goes by once every 1,000 years, and I want to be able to detect it. So I know that it's going by on December 1st. I know the general direction of the sky to look at. And so myself, being an amateur astronomer, I go to Toys R Us and I pick up an awesome set of Fisher-Price binoculars because I want to see this asteroid. So on the evening of December 1st, it's nice and clear outside. I point my Fisher-Price binoculars out to the black sky, and this is what I see. I see absolute darkness, punctuated with some random stars here and there. So sadly for me, I don't see an asteroid. So with this setup, I conclude that there is no asteroid, which makes me very, very sad. But when I was talking about this asteroid that I wanted to check out, I found out that one of my colleagues in the department is also an asteroid enthusiast, Dr. Andrew Llewellyn. And he also wants to observe this asteroid going by on December 1st. However, he takes a very different approach than me. He decides that he's definitely not missing out on this opportunity. So he is going to use one of the most powerful telescopes in the world that has ever been created to view this asteroid. So he is going to try and get his hands on the Hubble telescope. So December 1st rolls around, he knows the general direction where he needs to point the Hubble telescope. And this is what he sees. Holy smokes, huge close-up of this asteroid. I mean, he can see everything. He can see the mountains, the ridges, all the craters on the asteroid bearing, and he gets a very, very, very high resolution image of the asteroid. So he's happy. He's got a beautiful picture that he can show all his friends and family, and I guess he was a little bit more successful at finding the asteroid than myself. However, I also heard that somebody else in the research department is an asteroid enthusiast. Our lovely colleague, Dr. Bryn Robinson, but she takes a slightly different approach to this whole thing. She knows that it's going by on December 1st, and she knows the area of sky to point the telescope at, but her approach is to do some calculations. So Dr. Robinson calculates the approximate distance from the asteroid, from the Earth to the asteroid. She does this by going into the astronomical literature and the cosmological literature, so she knows that it's going to go by on this day around this time in this patch of sky, and it's going to be approximately X distance away from Earth. So she uses that information to select the right telescope with the appropriate telescopic power that she needs to detect the asteroid. So she goes to the telescope store, picks up this telescope for probably $1,000 or $2,000, and she points it out at the sky on December 1st, and what does she see? Bang, she sees the asteroid. So she's really, really happy. She takes a beautiful shot. It's not as high resolution as the picture that Dr. Llewellyn got, but nevertheless, she saw the asteroid. So She's not wasting her time with Fisher-Price binoculars, and she's not wasting a whole lot of resources with the Hubble telescope. So what does this have to do with power? So let's recap a little bit. So the approach that I took obviously had insufficient power. I used a pair of cheap Fisher-Price binoculars. I looked out in the sky, I saw nothing. So my setup had insufficient power to detect the asteroid, even though the asteroid was actually there. So in the end, I'm very sad with the little sad face there. On the other hand, Dr. Llewellyn, he definitely saw the asteroid, but his setup had, I would say, probably too much power. He definitely detected the asteroid, but it came at a great cost to him. He had to book flights down to the States. He had to book accommodations. He had to pay for food while he was down there. He had to rent out the Hubble telescope, which costs at $100 million operating costs a year, is about $12,000 per hour. And he also has to buy me some souvenirs before he comes back. So in the end, he is really sad. He found it, but he is sad because he's broke. On the other hand, Dr. Robinson, who's a very smart cookie, she took a more sophisticated, more planned out approach. She knew the distance. She calculated the type of telescope that she would need. So she calculated the power, the telescopic power that she would require to detect this asteroid. And the telescope was only $1,000 or $2,000, well within her budget. She got the picture and she is happy. So the point that I'm trying to make here is that this example has a lot of similarities to what power is within the context of research, which I will show you here. But before we start really diving into it, we want to talk about some important definitions. But just to back up a little bit, in this example, the asteroid would technically be the effect that we are looking for within a research context, and the power of the device that we use, whether it's the Fisher-Price or the Hubble, is the sensitivity of our study within a research context. So a couple important definitions. So what is power exactly? Power is a really complex topic, but it ultimately boils down to the sensitivity of a statistical test to detect an effect if one truly exists. So it's the probability of correctly concluding that an effect exists when it is truly there. Now, very intelligent, much smarter than me statisticians have determined that power, this probability, this sensitivity, should be set at approximately 80%, but it could be higher. And there's complex mathematical and theoretical reasons as to why 80%, but in general, it's just a reasonable balance between making false positives, which is your type 1 error rate at 0.05, and false negatives, which is your type 2 error at 0.20. So a lot of statisticians and methodologists have determined that having a power of about 80% is sufficient for most contexts, in most areas, and for most purposes. The effect is just the study result. It's what was found. It's the difference between two groups, if that's what you're interested in. It's the association between two variables, if that's what you're interested in. It's the predictive relationship between one variable and an outcome. And the effect size refers to the quantification. It's the quantification of this of this difference between the groups, the association between variables, and it's solely magnitude based. The effect size is completely independent of your sample, and it's just simply a pure estimate of what was found in your study. And a power analysis is the formal calculation that you can do to estimate the sample size that you need for your statistical analyses. And note that I said it's to estimate the sample size, it's not to determine a sample size. All power analyses and all power calculations are simply estimates. You will never get the exact right answer, but it will give you a ballpark as to what sort of sample size you need for your study. So why bother conducting a power analysis at all? There are a number of reasons. I was reading up on this over the past few days. There are so many different reasons, but I kind of boiled it down to these four, which I felt were some of the more important reasons. The first one in blue on the top left-hand corner is to determine the smallest sample size that is suitable to detect the effect that you are interested in. There are problems with undershooting your sample size, which I'll talk about very, very soon here, but there's also problems with too large of sample sizes. Too large of a sample size can potentially, in some contexts, introduce some ethical problems. For example, if you're testing the efficacy of a new therapy, certain therapies can be uncomfortable for participants, and particularly if the therapy is inferior to standard of practice. So because of that, research can be burdensome to some participants, particularly prospective studies where there's multiple follow-ups. You're getting people to fill out multiple surveys, you're getting them to provide, let's say, blood samples. You just want to be able to conduct a power analysis so you know the appropriate sample size that you need to find the effect that you're looking for. And also, there's also concerns accessing people's medical records, accessing to, if you have a sample size, if your power analysis tells you that you only need 100 people and you're accessing, let's say, 500 people's medical records, that itself can be a problem. And when you have very large sample sizes, overly large sample sizes, it also increases, there's also more financial and human resources that you may need to take into consideration that you may not have access to. There's also methodological problems. If your sample size is too big, that means that your study may have too much power, and that means that almost everything that you find will be statistically significant. So it's kind of like the Hubble telescope example. It's just so much power that every small little thing, every small little effect, every small little relationship will be statistically significant, and really highly so, but will be of very little clinical or practical significance. The second reason is that higher statistical power lowers the probability of making a type 2 error, which is a false negative. So that, in the asteroid example, that would be my situation. The binoculars that I used didn't have enough power, so I incorrectly concluded that no asteroid exists, when in fact it is there. So I made a type 2 error, I made a false negative error, and we want to avoid this in research. At least minimize it as much as we can. The third reason is that studies with low statistical power, with too low statistical power, will often lead to invalid conclusions about the meaning of your results. There's a number of problems that can happen with when your sample size is too small. For example, when you have a study, when you have a sample size that is too small, statistically significant results are more likely to be false positive results. So if you find something significant, you have less confidence in that conclusion, and you will conclude that a relationship exists, there's differences between groups when none exists, and then since your study is new and exciting and novel, it'll get published, and then the media picks it up, and then pretty soon it just becomes this knowledge that everybody thinks exists, but in reality is not true. And in my home discipline of psychology, some of the classic studies and some of the classic findings that were taught in intro psychology have been debunked by more modern research, because some of these studies are 50, 60 years old and were based on very, very small samples that have not been replicated, and more recently have been completely debunked. Low power can also result in inflated effect sizes, and overall your research will be generally unreliable, and unreliable research is generally kind of meaningless and wasteful. And when you have low sample sizes, the chances of your study being replicated is also quite low. And this is particularly important when clinical decisions are based on the results from such studies. So conducting a power analysis is a very important consideration. And the last reason, I think, is that doing a power analysis is just often a part of doing good research. It's a good way of ensuring that you have thought through every aspect of the study and the statistical analysis before you start collecting data. And once you think about it, you put a lot of effort into developing the background of a study, the research questions. You think a lot about the participants and how you're going to get them, and the measures that you're going to use and whether the measures are reliable. But when it comes to the analysis plan and the power analysis, people just seem to kind of skip over those parts. And I would say that they are just as important as the rest of your study aspects. So it's always a good idea to conduct a power analysis before you collect data. When should one conduct a power analysis? Well, for those of you who know me, you know I love memes. You always perform a power analysis a priori, which means a priori is just a Latin phrase which means from the earlier, from before. So you always conduct a power analysis prior to conducting your study. It is part of the planning phases. And you use the existing literature to estimate the size of effect that you're looking for, and you design your study accordingly. We'll go into a little bit more detail about this in the upcoming slides, but you don't calculate a power analysis once everything is done and all your data is collected. This is something that you need to be thinking about right at the start of conducting any research. And whenever I'm thinking about research projects, like that's usually the first one of the main things that I'm thinking about. I'm thinking about my measures and whether they're reliable, and the methods, whether it's a between groups design or within groups design, and how I'm going to power the study. And just kind of coming in with that mindset, I think just kind of helps guide a lot of your decision making. So the power analysis puzzle. Statistical power is one piece in a puzzle with several related parts. And in general, there's four main factors that go into doing a power calculation. Four main interrelated parts: the effect size, the sample size, the level of significance, and statistical power. And then there is the long forgotten other factor, which is other design aspects. So when it comes to the effect size, when you're doing a power analysis, you need to have some idea of the effect size. And this would be, as I mentioned earlier, the quantified magnitude of the effect that's present in the population. And depending on the type of analysis that you're using, your effect size can, there's so many different types of effect sizes. There's Cohen's D, Cohen's F, there's Pearson's R, Cohen's W, I believe it's called. There's so many different effect sizes. So that's one part of the puzzle that you need to try and determine. The other part is the sample size. In general, the greater your sample size, the greater your power. And of course, there's limitations to that. So the sample size just simply refers to the number of people in your sample, the number of observations that you're making. If you're doing animal research, that would be the number of rodents that you're using. If you're collecting blood in test tubes, each blood sample would be 1 unit of sample size. So sample size is another really important consideration. The other two are the level of significance and your actual statistical power. So the level of significance is the significance level that you use in your statistical test. So this refers to alpha. This is often set to 5% or 0.05. It can usually be a little lower than that, 0.01, 0.001. But the larger your level of significance, so when you move from 0.01 to 0.05, you generally have more power. And the last one is the desired power level of the study. As I mentioned earlier, it's typically 80%, which would mean that there's an 80% probability that you will detect an effect if one exists. And you can increase that if you want. You can specify a higher level. You can say that I want 90% power, or 95% power, up to 99% power. And the more you increase this threshold, the more power you will need in your study. So these four that I mentioned, the effect size, the sample size, and level significance and statistical power, they are four interrelated factors, and each is a function of the other three. So if three of them are fixed, the last one is completely determined. So for example, if you increase your effect size, but keep your sample power and your alpha fixed, you know that your sample size will have to increase. And the last and often forgotten one are other design factors that you also need to take into consideration. So there's so many of them, but just a few for you to think about. For example, the reliability of your measures, how many control groups you have, whether your groups are balanced or unbalanced, meaning whether you have equal number of participants in each, say in your treatment and control group, or whether they're really off balance. The number of follow-up periods, if you're doing something like a factorial ANOVA, typically the interaction effects require more statistical power than the main effects. Whether the assumptions of the model that you're using are violated or not, and sometimes when certain statistical test assumptions are not met, people switch from parametric to non-parametric analyses, and non-parametric analyses will usually have much lower power. Oops. I'll admit this, folk. Okay. And of course, things such as missing data. So there's so many different things that can affect the power of your study. Basically, almost any aspect of your experiment, of your study, will in some way directly or indirectly affect power.
Can you please explain statistical power again, just briefly?
Pardon?
Can you explain statistical power briefly again?
Can I explain statistical power again? What aspect of it?
I mean, because there are like four 4 points are like effect size, sample size, level of significance,
Okay,
and the
okay.
last one is just briefly.
Okay, yeah. So that just refers to your desired power level within your study. So, so you typically want the statistical power, like the probability of detecting a true effect if one exists, to be at about 80%. So for level of significance, we usually fixate that at about 0.05. For the power of your test, we usually fixate that at 0.8 or higher.
Okay, right.
Of course. Okay. Okay, switch screen here. There we go. And there are also some limitations and difficulties with power analysis. Very important ones to always keep in mind, and these are sometimes the things that keep me awake at night. So, for example, there are certain limitations when it comes to power analysis software packages. So some factors that indirectly affect power are not taken into account by certain software packages. For example, G-Power is one popular one that's used, and that is limited with respect to just the breadth, just the whole collection of analyses that you can power. Sometimes tests have like certain aspects of them that you can modify a little bit. Whenever you're doing let's say if you're doing a regression, there's different aspects of a regression which you can modify and which you can tweak. And some of these software packages just may not have those options available to you. And some software packages will actually undershoot your sample sizes. A classic example is logistic regression. For logistic regression, calculating power is notoriously difficult. And in G-Power, which is one of the more commonly used software packages, sometimes when I calculate power for logistic regression in G-Power, it will give me a sample of, let's say, 40 people. But I know from the literature that logistic regression usually requires at least a minimum of 100 people. So sometimes the software packages just may undershoot your sample sizes a little bit. There are also issues related to just real life problems. So whenever you conduct a power analysis, it will generate a sample size given a best case scenario. But a lot of these best case scenario estimates cannot reflect, they do not reflect the complexities that a researcher comes across while doing certain projects. For example, participants drop out. Let's say you had everything set up to collect data for 100 people, but you have low recruitment, or some of the measures that you were interested in turn out to be, some of the measures that you were interested in using turn out to be unreliable. So sometimes these things just don't work out, and you may have to recalculate power and amend your study. If you have to drop a measure, that means you'll have to go back and tweak the power analysis calculation. So, and sometimes, usually one thing that I find is that whenever I conduct a power analysis, the people that I'm doing it for are sometimes shocked as to how big of a sample they need. And that just happens to be the case for a lot of situations, especially when you're dealing with small and medium effect sizes. Sometimes the estimated sample size may be higher than the resources that you have. So whenever you're conducting a power analysis, you're always conducting it for let's say the Rolls-Royce version of the study that you plan to do, but real life happens and sometimes you're left with a Toyota Corolla, which is, it's an okay car. It'll get you from point A to point B, but the wheels may fall off in the process. Another limitation difficulty with power analysis is that it's usually based on a lot of assumptions and educated guesses. The power analysis and the sample size that it will estimate is not always precise. Sometimes you have to conduct several different power analyses, assuming different contexts and different situations to get a range of potential sample sizes for your study. For example, for my dissertation, which I'm currently working on, I conducted about 16 power analyses. And it's because I have 4 major groups of analyses, and within each group, I conducted 4 power analyses. So for one scenario, I have a lower end estimate, and then I also calculated a higher end estimate, and then a middle of the road estimate, and then a fourth one that was kind of between the low and the middle of the road estimate. So I conducted 4 possible scenarios for each of my 4 major analyses. So sometimes you're just left with dealing with a range of values rather than a precise, definitive number. And the last one, which I think is probably one of the most common ones, is that we don't know what the effect size is in the population. So you know your level of significance, let's say you set that at 0.05, you know your desired power, let's say you set that at 0.8, and you want to solve for your sample size, but you have no idea as to what the effect size is. So in these situations, it will require you to just to do your research, to go in the literature and start sifting through all the studies and trying to determine what that effect size could possibly be. So it requires subject-specific knowledge and a deep understanding of a field to get an idea of the plausible range of effect sizes. So in my home discipline of my background is forensic and criminal psychology, I know, since I've been doing that research for a long time, I know in general what the effect sizes look like in that discipline, but they may not translate to, say, neuroscience, or they may not translate to trials with certain drugs, with testing new therapeutics. So a lot of my time is spent reading studies in new areas and trying to get a sense, trying to get an idea of the effect sizes in that area, because what's considered average in one is not considered average in a different one. And a lot of times you are conducting a study that is completely new. Let's say you're testing the effect of a brand new intervention on children for, let's say, behavioral problems. But there's never been it's a completely new program. So it's a completely new program. There's no research on it. So you can't look into the literature and find effect sizes for that particular program. But I would say that even though there's no research for that particular program, we know from meta-analytic investigations of effect sizes that psychosocial, educational, behavior interventions with children tend to have effect sizes, let's say, of this particular range. So even though there's no direct research on your particular program, you can kind of look at other programs that are similar and try and estimate your effect size from them. And other times you may simply not know, have no idea as to what your potential effect size could be. So you can look into the literature and look for effect size guidelines. One of the more common ones is the effect size recommendations by Jacob Cohen, which were published in his book in 1988. And he goes through a number of different analyses, and he gives guidelines for small, medium, and large effect sizes for a number of different types of effect sizes: Cohen's D, Pearson's R, multiple R squared. And I would, if you try and go that route, I would probably recommend that you approach that with caution, because his recommendations were published in 1988, so they're kind of getting a little old, and some newer research, it's a little bit mixed, but they tend to confirm some of his guidelines, but some say his guidelines were probably a little optimistic. You should kind of tone them down a little bit. So often I see, when I'm reviewing research, I see people who don't know what the effect size, and they just assume a medium effect size. And sometimes a medium effect size could be overshooting it. We tend to be overly optimistic as researchers, and sometimes powering your study for a medium effect size in absence of any other information can be a little bit overly optimistic, and as a result, you may underpower your study. So that's all I have here, and I'll just go to here. So before I end, I want to just show you an example of a power analysis using G-Power, and tweak a few things and just show you how things change based on those tweaks. So this is G-Power. The icon for it is right here. And it's one of the more popular it's one of the more popular power analysis programs that you can get. It's free to use. You can download it absolutely for free. And I will show you how I would calculate a power analysis for a simple independent samples t-test. So you open it up. I'll just open up from fresh. There you are. So there's a lot of options here, here, and here, but they're also all compiled up here under tests. So you have a number of options for correlation and regression. You can do simple regression, multiple regressions, logistic regression, correlations. You can have a number of t-tests, ANOVA-based models, repeated models with interaction effects, multivariate models, I-square, McNemer's, Fisher's exact test. But we will do a power analysis for a simple independent samples t-test. So that would be right here. So we are doing an a priori sample size calculation. So we'll leave the tail at, we'll leave it at one tail test. And this is our alpha value, so we'll leave that at 0.05, and this is our power. So the default power in G-Power is 0.95 for all the tests. So I'm just going to turn that down just to our minimum threshold of 0.8. The allocation ratio of both our samples is 1. That means that the sample sizes are similar. And if I hover over this box, you can see that it gives me recommendations for effect size. So these are effect size conventions. These are based on Cohen's 1988 recommendations. So let's go. So let's in a study, I want to compare two groups on some outcome. I don't know anything about this research, so I'm just going to assume a medium effect size of 0.5. So everything is more or less entered for me, with the exception of just changing the power level. And I calculate that, and I can see that I need a sample of 102 to be able to detect a medium effect size. That would result in two groups consisting of 51 participants each. However, if in actuality, the effect size is a little smaller than that, let's say it's 0.4, you can see how my sample size increases by about 50 people, 78 per group, for a total sample of 156. If I decrease my significance level to 0.1, you can see how the sample size increases again. I put that back to 0.5. Let's say that my groups are unbalanced. So we'll go back to here, 156. Now let's say that my groups are unbalanced. So let's say that I have a control group and a treatment group, and for some reason, I expect my treatment group to be smaller. Let's say that just due to the nature of the treatment, I expect people to drop out, or maybe there's some very stringent inclusion and exclusion criteria to be in the treatment group. So let's say that our treatment groups are, let's say that my treatment group is half as small as my control group, 176. So you can see here that my control group is 117 and my treatment group is 59 for a total of 176. So again, this is just an estimate. In reality, when I'm actually doing this research, it's very unlikely that I'll have exactly 117 people in my control group and exactly 59 people in my treatment group for a total of 176. So that's what I mean by the power analysis giving you an estimate. This is like a best case scenario, but in reality, many things can happen, and I may not always end up with 176. And if I do, I may not end up with these